Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we are continuing our study of Chapter 7, which is equations of state, and we are looking at using the cubic equations of state. There are two of these that are the most commonly used. The first of these is the Soave-Redlich-Kwong equation of state, more fondly known as the SRK. It's a mouthful otherwise. This one was developed in 1972, and basically it's P equals RT over V minus B minus A, which is a function of temperature, over V times V plus B. The other one is the Pang-Robinson equation of state, developed in 1976, and quite similarly, P is equal to RT over V minus B minus A, which is a function of temperature. The denominator, however, is V times V plus B plus V times V minus B. If you were to graph these, you get these various curves here. So for temperatures above the critical point, you get a graph like this. For one below the critical point, you get something that has that more traditional cubic behavior. And when it exactly passes through the cubic or through the critical point, the cubic equation results in this. Basically, the critical point is a repeated root. The reality, however, if we plot this as pressure versus volume, this curve is our saturation curve, okay? Everything in the middle here is going to be unstable and immediately split into a liquid and vapor phase. So we have a curve that passes through here. Mathematically, what on earth does this mean? Because the curve is going to give me data that is going to, in reality, split into two phases. So there are a lot of facts related to the second law and some observations that people have made. If you take the intermediate thermodynamics course, we go into this in more detail. The molar volume decreases with pressure for an isotherm. That is, dV dP at constant temperature is going to always be negative. So that means that if I have a curve like this one here and it's negative, but then it comes back up and then comes down, that means that this portion here in the middle cannot actually be there, okay? That defies all of the theory. So we know this part is not physically possible, okay? This is called a stability criterion, and any stable phase is going to have this criterion, that as I continue to increase, or I guess if I decrease the pressure, the volume will increase. Okay, dV dP is negative. So this gets rid of this large portion of the weirdness of the graph, but I still have these other portions here and here that are also not physically possible, okay? This section here and this section here are what are called metastable. Now, you will observe metastable phases, but they don't last. What will happen is if you have something in this region or this region, it will appear as a single phase for a period of time, but if you leave it long enough, it will split into two phases. These will instantly split, okay? You can't have something held metastably in this region, okay? Thermodynamics is only defined for things that are at equilibrium. So therefore, the parts of the graph we are concerned about are this And this, with a little bit of interest in this portion here and here, and we know that this portion is going to be non-physical. In order to use these equations, we're going to need to determine the parameters A and B, and they can be obtained by fitting to whatever known data we have. Now, we might do it by fitting to an entire set of measurements over a wide variety of pressures, volumes, and temperatures, or maybe all we know is the critical point. Okay? The critical point is a saddle point. If you recall in the graph, that was the one where we had the repeated roots so that we had a change in the direction, but it wasn't either a maximum or a minimum. It's a saddle point. The first and second derivatives at that stage are both equal to 0. If we do that for either the van der Waals or the SRK or Pang-Robinson equations, we can solve for these constants A and B. For the van der Waals equations, so for the van der Waals, okay, not for anything else, A is 27/64 of r squared TC squared over PC, and B is r TC over 8 PC, okay? So if you have the critical data, you can estimate A and B for van der Waals equation. For the SRK and Pang-Robinson equations, it's a little more complicated. First of all, A is a function of temperature, so we need more data to estimate this. Ideally, we're going to use vapor pressure information, but as a proxy, we can use what is known as the Pitzer acentric factor. The Pitzer acentric factor is defined to be -1 minus the log base 10 of the vapor pressure divided by the critical pressure at the temperature where at the temperature that is equal to 0.7 times the critical temperature. So the vapor pressure is evaluated at this very specific point. And this is the Pitzer acentric factor. We can use this to estimate the constants in the SRK or Pang-Robinson equation of state. For SRK, A is A sub C times alpha. A sub C is 0.42747 r squared TC squared over PC. No problem there. Alpha is 1 plus M times 1 minus TR to the 0.5 power, the square root of TR. That entire expression squared. TR is T over TC. The actual temperature over TC. M is equal to 0.48 plus 1.574 omega minus 0.176 omega squared. Omega is that acentric factor that we just talked about. B is 0.08664 R times TC divided by PC. So you see here that what we need is the critical temperature and pressure, we need the gas constant, and we need that Pitzer acentric factor. Fortunately, those are all things that we can find in data books. For the Pang-Robinson equation of state, a very similar kind of expression. A is going to be AC times alpha. AC is 0.45724 r squared TC squared over PC. Alpha is 1 plus kappa times 1 minus the square root of TR, quantity squared. Kappa is 0.37464 plus 1.54226 omega minus 0.269932 omega squared, and B is 0.07780 R TC over PC. There's not a lot of difference between using the SRK and the Pang-Robinson. They have some minor advantages and disadvantages for different systems. It's mostly going to come in when we start looking at mixtures and thermodynamics too, when we'll have reason to use one or the other. The main thing is if you work at a company that says we use the Pang-Robinson as our model, use that, okay? It'll get you very good results. Now, how are we going to solve these? Because these are not linear equations, right? They are cubic polynomials. There are many, many ways we can do this, but one that we teach in our ChE 3111 course is the Newton-RAPHSON solution technique. There are videos to that in 3111, and in our course I'll give you links to those. But basically, if I have a first guess for what the answer is for x, I can get the next guess by taking my first guess minus the function at that first guess divided by the derivative of the function at that first guess. So all I have to do is take derivatives, right? So for the Pang-Robinson equation of state, I have those for you. The function is PV over RT minus V over V minus B plus AV over RT times 1 over V minus B, or V plus B plus B, V minus B. And the derivative of that with respect to V is P over RT plus B over V minus B quantity squared minus A times V squared plus B squared over RT times the quantity V plus B V minus B squared. Okay? Using this requires a computer, or you can do it in Excel. And again, I will provide a link to my 3111 video on this technique. So that concludes this lesson. Thank you very much for your time.